In this module, we will explore some basic knowledge of the power grid and renewable energy systems. Upon completion of this lesson, students should be able to list the basic components of the electrical power grid, describe the differences between the conventional grid and the smart grid, understand the challenges of integrating renewable energy, understand the concept of microgrid and operating modes, recognize the functions of the various domains of the electrical power grid, identify potential intra- and inter-domain interactions, identify critical communication paths in the smart grid control network, and understand security requirements for smart grid information and control network. Let's look at the evolution of electric power grid from centralized generation to distributed energy resources. The electric power systems in North America and Europe are probably the most complex systems ever built by humans. In the USA, the power system contains thousands of major generating units greater than 500 megawatts, millions of miles of transmission lines, millions of transformers, hundreds of millions of protection and control devices. In 2021, the generation of electricity in the US was about 4.12 trillion kilowatt hours. The reliability of the electric power grid is considered a national security matter. The demand and supplies of electricity must be matched in real time. Mismatches in electricity generation and load demand can lead to a major power outage and severe economic and safety consequences. To ensure reliable service, the electric power grid is broadly regulated based on two categories. Number one, wholesale sale and transmission of electricity in interstate commerce. The Federal Energy Regulatory Commission, FERC, is responsible for regulating this category. Number two, local distribution and sales of electricity at retail. States generally have jurisdiction over local distribution. Retail sales of electricity within a state from one entity to an end user. Note that reliability concerns for the electrical power grid are amplified by increasing the system's openness in order to integrate more distributed energy resources. The electric grid consists of three main sections: generation, transmission, and distribution. Conventional grid generation is based on bulk and centralized generation stations. The generated electrical power is transmitted using high voltage transmission lines from generation sites to locations close to the customers. The distribution network distributes the electrical power received from the transmission network to the end customer at suitable voltage levels. Generation, transmission, and distribution networks are connected through substations. Substations consist mainly of transformers to step up or step down the voltage level, switchgears, and protection devices. The end customers could be residential or industrial loads. In the conventional electric grid, loads are passive loads, which means they only consume energy and the power flows in one direction from the transmission to distribution to loads. Protections and control systems are developed based on unidirectional power flow assumption. Generation power plants are the most important components in the electrical power grid. Bulk generation mainly uses thermal or hydropower generation power plants. Thermal power plants convert thermal energy into mechanical energy using different types of steam and gas turbines to convert mechanical energy into electrical energy. Nuclear generation stations use fission reactions to generate thermal energy, which can be used to generate steam. Hydroelectric power plants convert the kinetic energy of falling water to rotation motion using a hydroturbine. Large steam plants are expensive to build but relatively cheap to operate, so they should be run more or less continuously as base load plants. Gas turbines are relatively inexpensive to build, but expensive to operate. They are most appropriately used as peak power plants. To convert mechanical energy into electrical energy, power plants usually use a synchronous generator connected to the turbine shaft. Synchronous generators are used in power plants to generate AC power at a fixed frequency equal to 60 Hertz in the US and 50 Hertz in Europe. The generator output voltage is not high enough to transmit the electrical power over long distance efficiently. To increase the transmission system efficiency, the output of the synchronous generator is connected to the step-up transformer to step up the transmission voltage and reduce the transmission current. The output of the step-up transformer is connected to the high voltage transmission line. Most of the transmission lines are overhead transmission lines. The reason for using overhead transmission lines instead of underground cables are the cost and ease of maintenance and repair. The cost of underground cable installation and insulation is huge in addition to the high cost of repair and maintenance. High voltage transmission lines are used to transmit the bulk generated power over long distance from power plants to locations close to the customer sites. The high voltage transmission level ranges from 200 kilovolts to 1 medium volt. Step-down transformers are used to step down the high voltage to sub-transmission level or medium voltage transmission to the range of 43 to 69 kilovolts. Distributed transformers reduce the voltage to a low voltage distribution level ranging from 13 to 4 kilovolts. Industrial customers and big facilities are usually directly connected to this voltage level and have their own service transformers to reduce the voltage. For a residential customer, service transformers are used to reduce the voltage to 120 volt level. Distribution networks are usually built using underground cables for safety, but in many cases, overhead distribution lines are used for cost considerations. The substation is a key element in the power system. Substations serve as a link between the generation, transmission, and distribution networks. There are several types of substations according to their location and functionality in the power system. A step-down substation links a generation plant to the transmission systems. A high voltage substation facilitates power flow between systems of varying high voltage levels. A step-down substation connects a high voltage transmission system to a sub-transmission system. A distribution substation connects the transmission or sub-transmission network to a medium voltage distribution network. Switching substation acts as a circuit breaker in transmission and distribution networks. The substation consists of transformers, switching equipment such as circuit breakers and switches, protection equipment such as surge protection and grounding systems, measurement equipment, and control equipment such as power factor correction capacitors and voltage regulators. To automate the substation operation, substations are equipped with Substation Automation System, SAS. The substation's automation system consists of measurement devices to measure voltage and current and feed the measurements to protection relays and control devices. Protection and control devices send control signals back to switchgear to control the operation and isolate any detected faults. Protecting and control devices are connected on the substation level to coordinate the operation and perform interlocking functions. Coordination and interlocking are necessary to ensure correct operation and sequence safety. Substation automation systems can be monitored and configured using human-machine interface and configuration workstations. In addition to the local human-machine interface, substations are connected to a remote control center. Old substation automation systems use analog signals and copper wires to hardwire measurement equipment and switch gears with control and protection systems. Hardwiring measurement and control signals is a tedious and costly process and hard to reconfigure. Modern substation automation systems use an Ethernet-based network to interconnect substation automation equipment. Analog measurements are connected to merging units, MU, which convert signals from analog to digital and share it over an Ethernet network. Merging units are connected to an Ethernet network called process bus and share all collected measurements with a high data rate. To ensure low latency and high throughput, merging units usually use layer 2 to communicate. Protection and control are programmed by Intelligent Electronic Devices, IEDs. IEDs are electronic devices equipped with processors, memory, and network interfaces to perform advanced control, protection, monitoring, and communication with the SCADA system. IEDs can receive measurements collected by merging units and send control commands over the Ethernet process bus using layer 2. To perform interlocking, coordination, and communication with the SCADA system, IEDs are connected to another Ethernet-based network called substation bus. All communication over the substation bus usually are IP-based protocols. The conventional electric grid is not only characterized by central generation, but also utilizes central control to control generation power plants and transmission networks. Substations and generation power plants are connected to centralized control centers. Transmission networks are monitored and controlled remotely using SCADA systems. Fiber optics and isolated networks are usually used to connect substations and transmission SCADA systems with centralized control centers. A Common Information Model, CMI, has been developed to ensure the compatibility of data definition and exchange between different applications, such as energy management systems, EMS, and demand management systems, DMS. On the other hand, the distribution networks in the conventional electric grid are not monitored by SCADA systems and have no or little communication. A simplified control network and SCADA system for the electric grid consists of IEDs to perform control and protection functions, RUTs to collect data from IEDs, communication processors to interface legacy devices with serial interfaces with Ethernet networks, communication links to connect RTU with central control, SCADA servers, historian, and application servers. This network is called the Operation Technology Network, or OT. The OT network should be isolated from the regular IT network of the utility company by firewalls and isolation zones. In addition to the SCADA system and RTU, an advanced metering infrastructure, AMI, is used to provide communication with smart meters. AMI is a two-way communication network that usually utilizes a mesh wireless network or power line communication to communicate with smart meters to collect power consumption and send information to meters such as energy pricing and control signals. Integrating renewable energy with a conventional grid based on centralized generation and central control is challenging. The renewable energy is distributed by nature, which means most of the renewable energies will be integrated into the distribution networks. Integrating renewable energy into the distribution networks will lead to a two-directional power flow, which requires modifications of protection algorithms. In addition, renewable energies could be installed on customer premises, which convert end customers from simple passive load to prosumer with the capability of consuming and producing energy. In order to control renewable energy resources integrated into distribution networks, communication and SCADA systems must be extended to cover the distribution networks. Centralized control is feasible with small numbers of bulky generation stations, but controlling large numbers of renewable generation units installed over a wide geographical area from a central location will be very challenging. New distribution control methods are required to simplify the integration and control of renewable energy resources. Modern electrical grid architecture should be developed to consider distribution, generation, distributed control, and extend communication networks to distribution. Successful integration of renewable energy into the electrical grid must address the following challenges. Control challenge. Management and control of increased levels of distributed and renewable energy sources. Interoperability. Challenge of integrating a wide variety of systems governed by different regulations and owned by different entities. Generation uncertainty. The variable nature of renewable energy sources complicates the process of balancing generation and demand. Demand uncertainty. Real-time energy forecasting and energy management systems for generation and demand balancing. Microgrid is a group of interconnected loads and distributed energy resources managed by a load controller. Microgrid works as a single controlled entity. It can operate in grid connected mode or disconnect from the grid and work in islanding mode. In islanding mode, microgrid utilizes local energy resources to feed the local load. In grid-connected mode, microgrid can sell to or buy energy from the grid based on available energy and local load demands. The microgrid concept provides a solution to manage distributed energy resources. Smart grid refers to the electrical grid, which is characterized by extending communication networks to cover distributed networks, smart meters, field devices, and distributed generation. More dependent on microprocessor-based devices and software, PMUs, IEDs, and PLCs, and connection with third-party networks, microgrids, and cloud systems. Now we look into the NIST reference model for smart grid operation. The National Institute Standard, NIST, adopted the approach of dividing the smart grid into 7 domains: customers, markets, service providers, operations, bulk generation, transmission, and distribution domains. Each domain encompasses smart grid actors and applications. Actors include devices, systems, or programs that make decisions and exchange information necessary for performing applications. Smart meters, solar generators, and control systems are examples of actors. Applications are tasks performed by one or more actors within a domain. For example, corresponding applications may be home automation or energy management. The customer domain is segmented into subdomains for home, commercial, and industrial. The energy needs of these subdomains are typically set at less than 20 kilowatts for homes, 20 to 200 kilowatts for commercial, and over 200 kilowatts for industrial. Each subdomain has a meter actor, energy management system or EMS, and an energy service interface or ESI. The ESI is the primary service interface to the customer domains. It may communicate with other domains. The EMS may provide auditing and logging for cybersecurity purposes. The customer domain is electrically connected to the distribution domain. It communicates with the distribution, operations, market, and service provider domains. The markets are where electrical energy is bought and sold. Actors in the markets domain exchange price and balance supply and demand within the power system. The boundaries of the market domain include the edge of the operations domain, where control happens, the domain's supplying assets, such as generation and transmission, and the customer domain. Communication between the markets domain and the supply energy domains are critical because balancing production with consumption is dependent on markets. Communications for markets domain interactions must be reliable, traceable, auditable, and must support e-commerce standards for integrity and non-repudiation. Non-repudiation means the sender of information is provided with proof of delivery and the recipient is provided with proof of the sender's identity, so neither can later deny having processed the information. Actors in the service provider domain perform services to support the business processes of power system producers, distributors, and customers, such as billing and customer account management. The service provider must not compromise the cybersecurity, reliability, stability, integrity, or safety of the electrical power network when delivering services. The service provider domain shares interfaces with the markets, operations, and customer domains. Communication with the operations domain are critical for system control and situational awareness. Actors in the operations domain are responsible for the smooth operation of the power system. In transmission operations, energy management systems, EMSs, are used to analyze and operate the transmission system reliably and efficiently. In distribution operations, distribution management systems, DMSs, are used for analyzing and operating the distribution system. Electricity generation is the process of transforming other forms of energy to electric energy. Other forms of energy may range from chemical combustion to nuclear fusion, hydropower, wind, solar radiation, and geothermal. The boundary of the bulk generation domain is typically the transmission domain. The bulk generation domain is electrically connected to the transmission domain and shares interfaces with the operations, markets, and transmission domains. Communications with the transmission domain are the most critical because without transmission, customers cannot be served. Transmission is the bulk transfer of electrical power from generation sources to distribution through multiple substations. A transmission network is typically operated by a regional transmission operator, RTO, or independent system operator, ISO, whose primary responsibility is to maintain stability on the electric grid by balancing generation with load demand. Examples of actors in the transmission domain include remote terminal units, substation meters, protection relays, and power quality monitors. Energy is procured through the markets domain, scheduled and operated from the operations domain, delivered through the transmission domain, to the distribution system, and finally to the customer domain. The distribution domain is the electrical interconnection between the transmission domain, the customer domain, distributed storage, and distributed generation. The electrical distribution system may be arranged in a variety of structures: radial, loop, or mesh as shown in the figure. Historically, distribution domain systems have been radial configurations with little telemetry, and almost all communications within the domain were performed by humans. The primary installed sensor base in this domain is the customer with a telephone, whose call initiates the dispatch of a field crew to restore power. In the smart grid, the distribution domain will communicate more closely with the operations domain in real time to manage power flows associated with a more dynamic markets domain. Smart grid will not only be a system of systems, but also a network of information networks. Within each network, a hierarchical structure consists of network technologies, such as home area networks, personal area networks, wireless access networks, local area networks, and wide area networks may be implemented. The network should provide the capability to enable an application in a particular domain to communicate with an application in any other domain over the information network with proper management control. Security is required to ensure that confidentiality, integrity, and availability of smart grid information, control systems, and related information systems are properly protected. Devices and applications in each domain are network endpoints. Examples of applications and devices in the customer domain include smart meters, applications, thermostats, energy storage, electric vehicles, and distributed generation. Applications and devices in the transmission or distribution domain include substation controllers, distributed generation, and energy storage. Applications and devices in the operations domain include SCADA systems and computers, or display systems at the operations center. Applications in the operations market and service provider domains are similar to those in web and business information processing. Because smart grid information and controllers flow through many networks with various owners, it is critical to provide proper security for the information and controls along the respective networks. Security for the smart grid information and control networks must include requirements for security policies, procedures, protocols, and authentication to protect information and commands in transit or residing in devices and systems, in addition to protecting infrastructure components and interconnected networks.